Hi, how are you?
Hello, hi Tommy.
I
Hi,
guess
how
I
are
think
you?
your email, I think the invite in the email got a little messed up with the panelist stuff. So okay, we're
Oh,
good.
okay. Yeah, thank you for letting me in. Um,
Absolutely. So we just opened up for everybody to come log in. If you want at this point, you could share your first slide just so we can confirm everything looks okay.
Yeah,
sure.
finally I get in. I had a
Great, thank you.
problem with you, E. I can't get in at the beginning.
Yeah, so, but thank you for solving the problem. So Tommy, do you want me to share my
Yes,
screen?
you can share your presentation material now. We'll confirm everything looks okay, and
Okay,
I see no problem. But then we'll do an introduction. Sure.
perfect. Thank you.
Okay. We'll just give it one more minute for people. We're waiting for Dr. Rickles to join. If he doesn't, Lang
I,
will do the.
I, I don't think he's gonna join, right?
Okay. It's up to him. He informed he might be here, so we're just gonna give courtesy minute.
He said his meeting with Cloud.
It's okay. We'll see. Okay. So let's see. Just another 30 seconds.
E, are you still in Stevens right now? Like if I'm visit you, I can see Manhattan.
Yeah, so today I'm working from home.
Uh,
Uh, yeah, so I usually go to office 3 or 4 days a week, and
mm.
1 day at home writing proposals and some other things. So today I'm working from home.
I was surprised you had like 170 journal publications. It's
Yeah, so my students
gorgeous.
and my students and colleagues have been working very, very hard. So it's
Especially
honor to.
you and I graduated at almost the same time, and you have like 170. I don't even reach 70s.
Oh, yeah, I think my collaborators and students they worked very hard for that. Um, so and also our maybe you you generate some more higher quality papers, right?
Nah, 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 nah.
Um,
No
All
one
right.
can compete.
Well, we will get started. I first of all, I want to just thank you for joining us and taking the time to present for us. This is our NHERI Lehigh seminar series that's been going on for years, where we give the platform to researchers like yourself to promote what you're doing through the NHERI environment and to reach out to the community to share the interesting stuff that you're doing. So with that, I want to just let our audience know that we're going to let our presenter go for the full length of the webinar. At the end of that, we will take questions and or any comments or questions through the chat or Q&A that you could use in the tool at the bottom. We'll keep everybody on mute. If you would like to talk during that time, you can raise your hand and we'll allow you to have conversation with us. But with all else done, Liang, if you'd like to introduce our presenter today. Thank you.
Okay, thanks, Tommy. My name is Liang Kao. I'm a nearly high research scientist. So, let me introduce a little bit on the nearly high seminars. So, because we normally host 3 to 4 researchers to present their research work during the nearly high seminars. It's based on the nearly network. So, Dr. Ibao is the second speaker for this year's. So his topic is smart fiber optic sensors technologies for structural health monitoring. So Dr. Yibao is an assistant professor in the Department of Civil, Environmental, and Ocean Engineers, and the founding directors of the Smart Infrastructure Laboratory at Stevens Institute of Technologies. His research interests include innovative sensors, materials, structures, robots, and machine learning technologies aimed at enhancing the sustainability, resilience, and intelligence of civil infrastructures. Prior to joining Stevens, he was a postdoc at the University of Michigan, Ann Arbor, and a guest researcher at the National Institute of Standards and Technologies. He is an associate editor of SE Journal of Bridge Engineering and Innovative Infrastructure Solutions, and an assistant editor of Engineer Structures. He has authored more than 170 peer-reviewed journal papers, accumulating more than 5,500 citations and an H index of 44. His scholarly achievements has earned various accolades, such as the 2022 Best Paper Award from the Journal of Engineered Structures. His research on fiber optics sensors has gathering financial support from the National Science Foundations, U.S. Department of Transportation, NIST, U.S. Department of Agriculture, New Jersey's Department of Transportation, and New Jersey's Economic Development Authorities. So right now, I would like to welcome Dr. Ebaus for his presentations.
Thank you so much, Dr. Tao. This is my great honor to present my recent research um, through the Lehigh webinar. It's a really great honor for me, and I hope I use this opportunity to communicate with our audience, and hopefully we have some useful discussions. Before I talk about the technical content, I want to briefly introduce the Smart Infrastructure Lab. So at the Stevens, we recently built the new structures lab with the structural testing capability. And more importantly, we have some sensing equipment for structural health monitoring, non-destructive evaluation, and we have some drones and robots for automated inspection of structures. And this is my group, the students, PhD students of my group, and the first two PhD students have graduated, and the third student will defend in the next week. So most of my work presented today was done by my students. The background problem of my research, as you know, the climate change is impacting civil infrastructure. It's causing a lot of problems, such as extreme weather and a lot of impacts on civil infrastructure. At the same time, civil infrastructure is aging. As we know, the grade of civil infrastructure by ASCE is pretty low, meaning our infrastructure is pretty fragile to climate change impacts. So it's very important to improve this situation. And currently, there are lots of efforts for improving climate change adaptation and mitigation. So the efforts can be mainly categorized in these two different areas. One is for the adaptation, another is mitigation. For the adaptation efforts, people have been developing larger and stronger structures, but those structures might increase carbon emissions. On the other hand, there are some mitigation efforts. For example, people propose to use more sustainable materials to build the structures, but some of those materials could reduce the mechanical performance and the long-term durability of structures. In general, there's a need to synergize the adaptation and the mitigation efforts instead of isolating them. So I propose to develop my group of mainly focus on developing sustainable and smart infrastructure. And this slide shows the bigger picture of my group's research. So we focus on improving human habitat under climate change by integrating the adaptation and the mitigation efforts through sustainable and smart infrastructure. And currently, our research mainly focus on three main areas, including sensors, materials, and structures. And also we use machine learning or deep learning methods for facilitating the research on sensors, material, and structures. So for the sensors, we mainly focus on AI-empowered sensor technology. And for materials, we have developed AI methods for automatic discovery and design of new materials. And for structures, we are developing smart structures adaptive to external events. So with the integration of sensors, material structures through advanced AI technologies, we try to improve the performance of structures. And for our research on sensors, we have developed different types of technologies, such as fiber optics to touch the structure, computer vision technologies to see the structure. And we also use electromagnetic wave-based sensing technologies to feel the internal condition of structures and use sound wave-based technologies to hear damages in structures. And today, my presentation mainly focus on fiber optic sensors work. And I will talk about our basic technology developments and also the applications of technologies for civil infrastructure. And the main themes include the research for normal temperature condition, high temperature corrosion, and some recent applications. First, the concept of using fiber optic sensors for smart structures. This was inspired by the biological systems such as human body. As you know, in human body, we have sensory nerves which can collect information of our body as well as the external environment. With the sensed information, the information can be analyzed by the central nervous system, which can understand the sensed information and make decisions for mitigating the negative impacts. And this information will be provided to organs or muscles to execute our decision, so that we can mitigate the impacts for human body. Inspired by this concept, we develop fiber optic sensors, particularly distributed fiber optic sensors, to collect detailed information of civil infrastructures. And fiber optic sensors are made using optical fiber. This picture shows the main components of a single mode optical fiber, which is composed of the glass core, glass cladding, and protective coatings. Those protective coatings mainly provide mechanical protection. Usually those coatings are made using polymer, but there are also some metal coating fibers. And for the fiber optic sensor, the light wave is guided through the total internal reflection at the core cladding interface because they have different refractive index. And because the cladding and the core are made using high purity fused silica or glass, the light wave can propagate along the optical fiber cable for a very long distance. Therefore, we can use fiber optic sensors as both distributed sensors and the transmission lines with the same cable. There are some important advantages of fiber optic sensors, such as the immunity to EMI effect, small size, lightweight, high chemical stability, temperature capability, and sensitivity. Also, fiber optic sensors can be operated remotely, and also we can multiplex different sensors for distributed or quasi-distributed sensing. And this talk will mainly focus on the fully distributed sensing capability. So before I talk about the distributed sensor, I want to very briefly introduce the main categories of fiber optic sensors, which could be categorized as grating sensors, interferometer sensors, as well as fully distributed sensors. The grating sensors and the interferometer sensors are also called point sensors because each sensor measures the information at a local spot where the sensor is deployed. So if you have a sensor, you can measure some data. If you don't have the sensor, there's no data. So compared with the point sensors, people have developed distributed sensors, which can provide continuous measurements along the whole length of optical fiber, and the measurement length could be longer than 100 kilometers. So this distributed sensing technology is based on light scatterings in optical fiber, including Rayleigh scattering, Brillouin scattering, and the Raman scattering. So in my group, we have used the Rayleigh scattering and Brillouin scattering based technologies because they usually have a higher sensitivity, higher accuracy, and higher signal to noise ratio because those scattering signal have a relatively higher intensity. So, for example, we have been using so-called PPPBOTDA technology. Uh, so when you use this technology, you can beam two lasers, light waves from the two ends of an optical fiber. For example, at the left end, if we beam an incident laser, this laser will propagate along the optical fiber and stimulates Brillouin scattering through the interaction of light and acoustic signals. And this Brillouin scattering signal could be sensed by the probe wave, which will carry the backscattering information. So if there's any strain or temperature change at a certain length of the optical fiber or distance of fiber optic sensor, then the backscattered signal will reflect this strain or temperature change by showing a Brillouin frequency shift. And at normal temperature, this frequency shift can be related to the strain change and temperature change using a linear equation. So this equation could be applied when the temperature change is small. So it's a linear equation, very simple, and we can calibrate the sensitivity coefficients in this equation. Well, the concept is pretty straightforward. And how about our research? So we have made some contributions to the basic understanding of distributed sensors, including the strain transfer behavior, high temperature sensing, and the corrosion sensors. We also applied those sensing technologies for civil infrastructure, including normal temperature applications and high temperature applications. So first, if we want to use the fiber optic sensor to measure strain, for example, we want to measure strain in concrete. So we can embed the sensor inside the concrete during concrete casting. Then after concrete is hardened, we can measure the strain change, right? So, but if you recall in a previous slide, I showed that the fiber optic sensor has a protective coating. For example, we use polymer coating to protect the optical fiber because the fiber sensor, the sensing part is the glass fiber. The glass is fragile, right? We have to use some materials to protect the fragile glass. So if we use the polymer coating, then are we measuring the real strain using the glass fiber? So in fact, there is a shear deformation in the polymer coating, right? Because of this shear deformation, the strain sensed by the glass fiber will be different from the real strain in the host matrix, like a concrete matrix. This is known as the strain transfer effect. This effect has been well studied for point sensors. So point sensors can be considered as very short length. Within its length, the strain field in the host matrix can be considered as constant strain. Well, this problem can be solved through a mechanical analysis. But we focus on solving the problem for distributed sensors with a very long length. And because of the long length, the strain field for the fiber sensor at different length distance, the strain field could be different. So we derived this governing equation, and then we try to solve this governing equation by defining the boundary conditions. First, we consider the simplest case, which is uniform strain field. This is very similar to the strain transfer problems for point sensors subjected to constant strain field. And in this case, we assume the fiber optic sensor is embedded in a uniform concrete cylinder. And if you apply uniform stress, like a compression to the cylinder, then we can easily solve this governing equation. And we generated the plots. And you can see that if the sensor has the point A and point B at the two sides, two ends of the cylinder, then at each end, there's a development length. Within the development length, the measured strain is lower than the strain in the host matrix. So this is similar to the development length for reinforced concrete. Because of the development length is necessary to correct the sensing results. And for this simple case, we can do this correction based on the solved equation. But how about non-uniform strain fields? Because distributed sensors are very long, and at each length, the strain could be different. And this could be very complicated strain field in general. So solving this problem was a challenge, and my group solved this problem by representing the arbitrary strain field using a mathematical formula, and we solved this problem. And this work has been published. Based on this work, we were able to use a distributed sensor to measure continuous strain fields. But then we realized that in many cases, the strain field condition is not continuous. It could be discontinuous. For example, if you have a crack, the crack will cause discontinuous strain field conditions. At first, we were concerned that the fiber optic sensor will be damaged because of the crack, right? Because the glass fiber is very fragile. But we did the testing and we found that the crack didn't rupture the fiber optic cable because because debonding could happen between the glass fiber and the polymer coating. And here you can see a SEM picture showing the debonding at the interface between the glass fiber and polymer coating. So because of this debonding behavior, the abrupt, very sudden deformation at the crack opening will be averaged over a debonding length, which is longer. So therefore, we could use fiber optic sensor to actually detect and locate cracks. And we can use a single sensor to map a lot of cracks. So for example, here we have two cracks at crack A, crack 1, crack 2. At each crack, the fiber optic cable was stretched to a higher strain level as shown by the red color. So because of this increase of tensile strain, we could detect peaks in the strain distribution along the length of the optical fiber. So the position of the peak in the measured strain distribution reflects the position of the crack in the structure. And also the magnitude of the peak is related to the crack opening width. And we did a lot of experiments and we found that we could even quantify or estimate the crack opening width because theoretically, there's a relationship between strain and deformation, right? If we do the integration within this range, we could quantify the crack opening width. And we found that we could quantify the crack opening width within a very large range. This work has been reported in these two papers. And then we conducted further research to understand the interfacial mechanics for fiber optic sensors undergoing the interfacial debonding. So we did the single fiber pull-out testing to characterize the interfacial mechanical property, and then we developed a mechanical model to describe this interfacial debonding. So with the mechanical model, we were able to predict the debonding behavior pretty accurately. And this really enhanced our understanding of the interfacial debonding behavior and also provide us a theoretical basis to quantify the crack opening width. This work has been published in a paper. So I will not elaborate the details, but if you have interest, you can either read this paper or talk to me later. So in summary, we have developed the two-way strain transfer analysis approach. The forward strain transfer analysis is that if we know the real strain field, then we could calculate the strain sensed by the optical fiber, right? We can apply the strain field as the boundary condition to solve the governing equation for the strain distribution in optical fiber. But in real applications, the problem is the inverse problem because we do not know the real strain field. What we know is the strain distribution measured from the fiber optic sensor. And we wanted to determine the strain field in the host matrix. So this is the inverse problem. And we developed a method based on optimization technologies to solve this inverse problem. So with this strain transfer approach, we are able to measure the arbitrary strain field using a distributed sensor. And then we have applied the technology to several applications, including material characterization and structural testing. So this slide shows an example for the material characterization. We use the fiber optic sensor to characterize the autogenous shrinkage for ultra-high performance concrete. As you know, the shrinkage of concrete could cause a lot of problems, such as the early degradation of structures. According to ASTM standard, the autogenous shrinkage of mortar can be measured using a corrugated tube. And we could measure the length change of this tube over time. So when we use this method, what we measure is the length change using this diameter, and we can solve the strain or the shrinkage strain of the mortar by averaging this length change over the length of the specimen, right? So when we do this, we assume the shrinkage is uniform. But is the shrinkage strain really uniform? We had this question. So we tried to use the distributed sensor to measure the shrinkage strain. And we found that, in fact, the autogenous shrinkage in mortar is not uniform. And there are many factors that could cause this non-uniformity. And what we can see from this figure is that the shrinkage strain can be different along the length of the specimen, and also we detected a micro crack from the strain distribution. And after the testing, we cut the specimen, and indeed we found a small crack there. But according to previous method, we will overlook those effects and therefore generate a very large scattering of data. But with this method, we can better characterize materials. And then we extended the application to monitor structures. For example, we have tried to monitor cracks in pre-stressed concrete beams. Well, pre-stressed concrete is often used in large-scale structures like bridges in order to minimize concrete cracks. And in this testing, we deployed a distributed fiber optic sensor with both inside of the concrete and also on the surface of concrete. So for the inside installation, we did the installation before concrete casting. And then after concrete is hardened, we attach we attach another fiber optic cable on the surface, as shown by the green color curves. So we apply the 4 points of bending to this beam, and when the load increased, at the very beginning, we measured the strain change, and then as the load was increased, we were able to detect some peaks from the fiber optic sensor, and each of the peak represents a crack in concrete. And when the applied load increased from 30 kilonewton to 61 kilonewton, as you can see, the more peaks were generated, and for existing peaks, the magnitude increased with the increase of load. So this means the distributed sensor was able to monitor the initiation and the growth of cracks. And after we generate the strain distribution, we could replot the strain distribution because we deploy the sensors at different locations. we can replot the strain distribution, and we can use a linear interpolation method to estimate the strains between the different lines. In this way, we were able to generate two-dimensional plots to visualize the initiation and the development of cracks in concrete beam. This gave engineers a method to easily visualize the damage conditions in structures. But when we try to use this technology for real bridges, we realize there are some challenges. One of the most important challenges is that the distributed sensor will give us a lot of data. So for example, if we have a 1 meter long optical fiber cable, if the spatial resolution is set at 1 millimeter, then in 1 meter cable, in each measurement, you get 1,000 data points, right? And if we set up a sampling frequency of 10 hertz, that means in 1 second, you get 10,000 data points. And for bridge applications, the length is definitely longer than 1 meter. It could be hundreds of meters or even longer than 1,000 meters. Then the data is very, very large, right? Very large data volume causes problems in data analysis. So if we assign human engineers, it's almost impossible to monitor the initiation of new crack and the development of existing cracks. So how to solve this problem? We have developed some machine learning methods to analyze the data points automatically and very efficiently. So we could achieve real-time or near real-time monitoring. So this the development of machine learning technology for automatic sensor data assessment or understanding was also inspired by the biological system. Our central nervous system can analyze and process the data from the sensory nerve system and also generates decisions. So this automatic and intelligent decision-making process is very important for large-scale structures subjected to various changes, including the internal degradation and external effects. So we developed two main methods for the data analysis. The first method is relatively simple method based on peak detection. So because when we have a crack, we will generate a peak in the strain distribution, and we propose to integrate the peak detection and some other technologies to achieve crack detection, quantification, and visualization. So based on the machine learning results, we could analyze, understand the sensor data automatically, and this processed data could be used to generate a 3D digital twin model for the structure. And this model was related to our distributed sensor system. So this digital twin is a live digital twin that can update in real time. The second method is to utilize the deep learning technologies. Well, when we do the measurements from the distributed sensor, we measure the strain versus distance. So this kind of curve was converted to RGB image. This kind of RGB image was then analyzed using some deep learning technologies. And we also applied the transfer learning to improve the accuracy. So eventually we were able to use machine learning methods to automatically analyze the distributed sensor data for monitoring cracks. And then we extended the application to monitor interfacial delamination. This is another challenge for the layered structures, such as the bridge overlay, bridge deck overlay, or a pavement overlay. So UHPC has been used as the overlay material because of the high mechanical strength and durability. However, in real projects, engineers have identified the early age delamination and the interface between the overlay and the substrates. And this overlay delamination was related to early age shrinkage and the change of relative humidity. But there was a lack of effective methods to monitor the interfacial delamination. So some researchers tried to use displacement sensors like LVDT, but in field application, it has been difficult to use those sensors. So we propose to use distributed sensors to investigate this delamination problem. And the distributed sensors could be in situ sensors for real-time monitoring. We propose to install the distributed fiber optic sensor following this pattern. The purpose was to make a relatively small specimen for laboratory testing. And we wanted to make sure that the fiber optic cable passed through the interface back and forth, forming a lot of intersection points. And at each intersection point, if delamination happen, for example, at this point, before delamination, this point is 1 point A and B. And after delamination, this point is separated to point A and point B. And the fiber optic cable at this position will be stretched to a higher strain level. And therefore, we could detect some peaks in the measured strain distribution. Well, this installation method could be modified in real applications. For example, we could increase the distance between or the spacing between adjacent intersection points, and then the whole fiber optic cable could be embedded inside the concrete. The key point is that the fiber optic cable can sense the strain distributions along the entire length, and the delamination points could be detected at some sharp peaks because of the discontinuous strain field. And this strain distribution could be replotted to show the delamination condition because we know the positions of the intersection points in the physical specimen. Then we can replot, we can separate this strain distribution into different segments and then replot that to show the delamination condition. So in this figure, the red color refers to delamination. You can see that delamination occurred at the two ends of this specimen. And in the middle, blue color shows no delamination. And this delamination estimation results was validated by a dye penetrant testing. So we immersed the specimen in dye solution, and after a certain time, we removed the overlay, and then we could visualize the interface condition. So as you can see, in the middle of the specimen, there was no delamination, and at the two ends of the specimen, we observed the delamination. This is consistent with our fiber optic sensor results. And then to further understand the early age delamination problem, we created a three-dimensional finite element model. In this model, we used the material properties obtained through the material testing. And then we, as you can see, the material properties change over time, right? So if we apply the material properties to this finite element model, we could predict the stresses at interface. And also, if we have the interfacial properties of the interface, then we could predict whether delamination will happen. And if it happens, what is the severity? So as you can see, at a very early age, well, actually delamination started to happen at 6 hours after the final setting. And then when the shrinkage increased over time, we can see that more delamination happened. This delamination area increased over time, and eventually we could predict the final delamination condition. With this computing technique, we were able to guide the design of ultra-high performance concrete. So we could strategically deal with the trade-off between shrinkage and the mechanical properties. So eventually, my collaborator, Professor Wina Meng from Stevens, her group developed version of ultra high performance concrete with lower shrinkage but higher bond strength. Eventually, they eliminated interfacial delamination. Another application is to use the fiber optic sensor to monitor buckling of thin wall structures, which is often used, for example, thin steel plates used in bridges or buildings, and also for aerospace engineering, thin wall structures are also very often used. In this research, we developed a mathematical method to understand the strain field measured from the distributed sensors. So, for example, if we have thin aluminum plates, we can deploy sensors in this pattern, and we can measure the strain distribution. So, by converting the strain distribution into the autoplane deformation of the plates, we were able to estimate the buckling severity. And we also validated this measurement results using point cloud data from computer vision measurements. And as you can see, when the applied load increase, we were able to detect the initiation and the development of buckling. And from 3,900 to 4,100, the load was increasing and the buckling shape was also increased. And we also captured the descending stage. When the load started to decrease, we can see that the buckling kept increasing. So we were able to use this method to monitor the whole process of buckling. Those applications mainly focus on laboratory testing. So how about the field testing? We have collaborated with Minnesota DOT and applied distributed sensors to some field projects such as the pavement overlay project. In this project, we used the fiber optic sensor. We embedded the fiber optic sensor during concrete casting, and then we use the sensor to monitor the temperature change, strain change, and we also apply the track testing, track load to generate the cracks. And the sensor captured the cracks successfully. And the sensor data have been used to improve the design of concrete and the unbounded pavement overlay. So then I will briefly talk about our research on fiber optic sensors for high temperature applications. So we collaborated with engineers from National Institute of Standards and Technology to develop the high temperature fiber optic sensing technology. So one of the important findings from this project was that because the Young's modulus of glass is dependent on temperature. See here, the Young's modulus increase with temperature, and this temperature-dependent property caused the problems when we use the sensor in high-temperature applications because this generated the non-uniform strain and temperature fields. So this affected the measurement accuracy. So to solve this problem, we conducted the thermomechanical analysis. I'm not going to elaborate the mathematical work here, but eventually we were able to relate the strain value to the length change of the sensor. Therefore, we can improve the calibration accuracy. After we calibrate the sensitivity of the sensors at the elevated temperature, we apply the sensors to measure both temperature and strain. And a very interesting phenomenon we observed was that the sensitivity coefficients, like strain coefficients, was dependent on temperature, actually, which means the linear equation I showed you at the very beginning of this talk will not be valid anymore when the temperature is high. And but based on our calibration work, based on the thermomechanical analysis, we were still able to calibrate the strain and temperature sensitivity coefficients. However, when the temperature was higher than 850 Celsius degree, the measurements became unstable. So this was because of some kinetics of the residual stress within the fiber optic sensor. The residual stress was generated during the glass fiber fabrication process, and at high temperature, the residual stress would be released and therefore affect the microstructure of the glass fiber. So we proposed a method based on thermal annealing technique to stabilize the residual stresses. And therefore, we increased the thermal stability of the fiber optic sensor. So after that, we were able to use the sensor to measure temperature higher than 1,000 Celsius degree. Therefore, the sensor was able to do the measurements in fire hazards. Then based on this research, we applied the technology to fire hazard applications in the National Fire Research Lab. We have applied the sensor to both concrete and steel. So we burned the structures within fire, and we measured the temperature distribution for the concrete, steel, and steel concrete composites. This measurement was very important because based on the temperature measurements, we could conduct thermomechanical analysis more accurately without having to predict the temperature field. Because to predict the temperature field involves a lot of assumptions. As you can see, the temperature field within the material is actually pretty complicated. It's not uniform, it's not symmetrical. This method can greatly improve the thermomechanical analysis accuracy and efficiency. And based on the research for small-scale composite structures, so we have applied the technology to some full-scale specimens for the floor beam project. In this project, we installed the fiber optic sensors inside the concrete slab and also attached to the surface of steel beam. But steel beam was covered using some sort of materials for fire protection for the steel. So the fiber optic sensor was actually in direct contact to the steel, but covered by the fireproofing composite. So we did this thermomechanical analysis. We burned the specimen in fire. At the same time, we applied the mechanical loading to the specimens. So we were able to measure the temperature and the strain change of the composite specimen. Then we also did some research to develop the fiber optic corrosion sensors. Because of time, I'm not going to elaborate those work. But based on those research, we found that the fiber optic sensors could be applied to monitor steel corrosion, and we developed the empirical data, empirical formula, and some theoretical models to relate the fiber optic sensor data to the corrosion severity. And we also evaluated the impact of fiber optic sensors on the interface between steel bar and concrete. So we found that the installation of fiber optic sensor, if the installation is well designed, it will not reduce the bond property. And we have applied this technology to several types of materials and structures. So this enabled us to monitor steel corrosion. And in addition to the monitoring of reinforced concrete structures, we also applied this method to monitor the corrosion for pipeline. Further, we developed a machine learning method to automate the sensor data analysis for monitoring corrosion for steel bars and pipeline. So with this capability, we could generate a digital twin model, which could be updated using the sensor data for different types of structures. And most recently, we collaborate with New Jersey DEA to monitor offshore wind turbine. Currently this is still in our laboratory testing, but in the future we plan to apply this to real structures. and we have been using distributed sensors to monitor specimens simulating offshore wind turbine, including both the superstructure and the foundation, and also the submarine cables. Also, we have applied this technology to monitor the large-scale 3D concrete printing process because we could install the distributed fiber optic cables during the printing process. Then the installed sensors will serve as in situ sensors for long-term structural monitoring. Yeah, because of time, I will just stop here. And our research has been funded by different federal agencies, state DOT, and private companies. Because I couldn't elaborate all the details due to the limited time, I put my email here. So if you have any questions, please feel free to send me emails. That's all. Thank you very much.
Thank you, Yi. Appreciate you spending the time and going through your research. I'm going to go look at the questions that we have. We do have one from Amy in the question and answer, and I'll read it. How did you keep your fiber optic sensor from moving during the casting of your concrete beam?